So let me show you how to perform LSDA+U calculations first. And as an example, we take the system which I showed you before, nickel oxide. We can have a look at the crystal structure here. So the lattice vectors, we have two inequivalent nickel atoms in the unit cell, as well as two oxygens. So the magnetic moment on the first nickel will be pointing up, and on the second one it will be pointing down. I have already set up the calculation. We have a k-point mesh, 12 times 12 times 12. Computational setup is quite standard. It's done according to the principles which I explained to you in the previous videos. I have placed 3s and 3p states of nickel into core. Here we are. So it allowed me to get rid of energy set 2. I have only one energy set, and what's specific here is that I also lock the linearization energies of 3D states to be in the center of gravity. It is probably a good idea to do it because we will do projections on the nickel 3D states, and if the linearization energies are placed properly, then we have higher chance to get a good representation of these orbitals. But apart from that, the setup is quite standard. And what we can do, we can immediately run the first iteration. So let me see, I have 49 K points. So I can run on 39 cores. It looks good. The first iteration has already been done. We can have a look at the out file, and we can check the magnetic moments. On the first nickel atom, it indeed points up. We have 1.36 Bohr magneton. And on the second nickel atom, it's just the opposite. And the total moment is 0. So what I suggested is that we immediately, after the first iteration, we add a Hubbard U term. And this is very easy. We just have to create an additional file called green.inp. And as soon as this file is present in the directory, the code will automatically add the U term. Here we have to give a bit of information where we want to apply the U, what is the value of U and Hund's J, what is the double counting, etc. And we define the correlated cluster. So cluster tag defines the local impurity. We will have one atom, and we will define the U matrix specifying two values, U and J. So since it's two values, we put 2 here. Alternative choice is free, and then you have to specify the Slater integrals, F0, F2, and F4. Okay, the parameters will be specified in electron volts, so we put EV here. And now we have to define our orbitals. So we specify the type, L quantum number, energy set, site, and the basis. The default is 0, which means that we're gonna use spherical harmonics. And now we can specify U and J. So for nickel oxide, let's take U equal to 8 and J equal to 0.9. And if you have several sites which belong to the same type, you don't have to specify each and every one of them. It's just enough to specify the first site, and RSPt will automatically apply the same U on all other sites. And in the last line, we specify the solver. In our case, it's DFT+U. It's choice 2. Next, we have to specify the double counting correction. And we take fully localized limit, which corresponds to number 2 here. And finally, we have to specify the mixing of self-energy from one iteration to another, because usually when we run DMFT, we have to gradually converge self-energy. In case of DFT+U, we don't have to converge it. We basically calculate it on the fly and can immediately apply it. So we put the mixing parameter to 1. So this is nickel up. We copy this structure and we make the same setup for nickel 2. And the only difference is that it has a type 2. In principle, that's it. That's sufficient for the code to run the calculation. So we can just save this file and run one more iteration. We got a couple of more files. Now we're going to have a look at the out file. And we see that we got a new block, a subroutine called Brianna. Here you can see that what the code did, it converted U and J values into the Slater integrals. And now these values are specified in Rydberg. We have one Matsubara frequency. In case of DFT+U, the self-energy is static, so it's the same for all frequencies. These flags tell us that the calculation is charge self-consistent. So this is the Hamiltonian projected onto correlated orbitals. The local overlap, in parentheses it says close to 1, so that's always good to check if you work with a new system, because it shows you how close your orbitals to being orthonormal. And in our case, you can see that it's very much so. Okay, now this information for the second impurity. Local density matrix has been calculated for the d orbitals. It's here. It's a 10 by 10 matrix, again, like Hamiltonian. And certain observables have been calculated as well. So we have the occupation, and it's close to 7.8 electrons. The nominal occupation of nickel 2+ ion is 8, so it's pretty close. In our case, this is the value projected onto Moffington sphere, so it makes sense that we don't exactly get 8. The components of spin moment were also calculated, and they are listed here. The spin moment is roughly 1.3 Bohr magneton, but this is just the first iteration. And the orbital moment is 0 because we don't have any spin-orbit coupling. Then we have the same information for nickel down, and we can see that the spin moment is minus 1.3 Bohr magneton. So this is the moment calculated from the projected local density matrix, and it only has the contribution from the d states. You can compare this number with the one shown below in the end of the file, and the total moment per nickel is 1.76 Bohr magneton, and the difference comes from the sp electrons. Now we can exit and run this calculation to self-consistency. Great, looks like it's done. So we can have a look at the summary of DFT+U part. The self-energy is very well converged. The total moment is still 0. Very good. And this is the new value of the Fermi level. Okay, let's have a look at the out file. Now, the magnetic moment is, close to 1.74 Bohr magneton per nickel. We can compare this number against what's calculated from the d orbitals, and it's pretty much the same. So indeed, at the first iteration, we got quite some difference between these two values, but it was so because the density was non-converged. Right now we can see that the magnetization is formed 95% by the nickel d orbitals. We can plot the density of states, for example, and this is very easy. What we have to do is just to add one more line in our green.inp file. It can be placed anywhere. We use the tag spectrum, and we say that we would like to see the dose in electron volts. The dose will be printed with some values of smearing and in a certain energy window, which will be taken by default. So we run just one iteration and we got new files such as DOS and PDOS. DOS.dat file contains total density of states as well as projected onto spin up and spin down channels. And if we look at the PDOS of the nickel up, again spin up and spin down, as well as projections onto free spin directions. So let us print the projected density of states on nickel d states of the first nickel atom, so type 1 here. Here it is. We have now printed all the columns in the out file, but what we actually need is spin up and spin down. So this was the second and third column. And the gap is quite substantial. It's definitely 4 eV or maybe even larger. And now we will try to perform LDA+U calculation. We have to start from spin unpolarized density. The double counting is also non-polarized, and magnetism arises solely from the U part. In practice, we will have to do several modifications in our setup, such as, first of all, we have to enforce that the density is actually unpolarized at every iteration, and this is set by the flag 11 in the print array. We also have to make sure that the double counting is the same for both spin channels. For this purpose, we use the special debug flag, spin average double counting. And finally, we have to break symmetry for the starting self-energy. So we use the tensor moment to break the symmetry, and there is a special notation for tensor moments. You can look it up in the manual. This one would correspond to sigma z Pauli matrix. So it will shift spin up states up and spin down states down by a certain amount, and this amount is given by the prefactor x, which we also specify in the input file. In case of nickel oxide, since we have two different atoms with opposite spin directions, here the factor x will be either positive or negative. So let me show you how to perform LDA+U calculation. And I have created a separate directory where I basically copied everything from LSDA+U calculation. And now we have to do several modifications. The first difference is that our starting density has to be unpolarized. So we go to the atom directory and we modify the data files for nickel up and nickel down atoms. So here we used to have a spin polarization. Now we remove it. We say that the states should not be spin polarized. And we do the same for the second type of nickel atoms. We regenerate the atomic density. Now we have to change the print array, and we go to flag number 11 So it's quite convenient here. So this indicates that it's flag number 10. So the next one is 11, and we put it to true. Good. So we make data. For a moment, we remove green in file. I just would like to run one iteration and make sure that I have a non-polarized density. Great. That's exactly what we need. Everything is ready to start LDA+U calculation. We can copy the green.in file from LSDA+U calculation. For the moment, we don't produce spectrum because we do it at the very end. Otherwise, it just takes time. And what we have to do here is to make sure that we break the symmetry. First, we have to create the type of symmetry breaking, and we do it with tensor moments. We call tensmom. We say that with tensor moments we would like to apply symmetry breaking, and we break the symmetry according to this tensor moment, which corresponds to SZ Pauli matrix. And here we now will specify the magnitude of the symmetry breaking. So we have to push spin down states above Fermi level, and for the other type of nickel atoms we will have to do the opposite, because we want a magnetic moment to point in the opposite direction. So let me put 0.5 here and minus 0.5 here. What we also have to remember is that we have to ensure that the double counting is unpolarized. So we set up the debug flag, spin average double counting. This way, the double counting becomes just a number, which is the same for all orbitals. Let's run only one iteration. Let's have a look at the out file. And you see there are no magnetic moments calculated from the density. So this is totally normal. On the DFT level, we are not supposed to see any magnetization. If we scroll up and we go to the DMFT part, here we can see that the first nickel atom has a magnetic moment of 1.8 Bohr magneton, and it points up, and the second nickel atom has the opposite magnetic moment. So locally, these magnetic moments indeed exist, and this is just perfect. So it means from now on we could just run this calculation to self-consistency. But remember that here at the first iteration we broke the symmetry, and we don't have to do it anymore. So this flag, it was only important at the very first iteration. So now we can just run this calculation to self-consistency. Looks like the calculation has converged. Indeed, we reached a very low FSQ value. If we also check the last DFT+U iteration, the self-energy is converged, the spin moment is 0. So far so good. Again, we look at the moment. Very good. The density still looks unpolarized, but locally there are magnetic moments, and it's similar to what we had in LSDA+U, but not exactly the same. So now we can also produce density of states. So we got the density of states files. And I think what would be interesting is to compare our results from LDA+U and LSDA+U. So let's have a look. And you see that there are indeed differences. So now we don't see the spin character, but if you remember, this peak was of pure spin down character, and this peak was of spin up character. What you can see is that in LDA+U we got smaller value of a gap, and in LSDA+U the spin down states are pushed a little bit higher. I hope you enjoyed, and I hope it became more clear how to perform LSDA and LDA+U calculations in RSPt. See you next time, but until then, enjoy RSPt.